Every time you tap a video on your phone or, send a quick email, your data might literally travel to outer space and back before the page even loads.
Yeah, it's pretty wild when you actually think about it.
It really is. I
Wow.
mean, welcome to today's deep dive into the hidden architecture of human connectivity. We're using some uh, really great insights from Professor Messer's CompTIA plus network training materials to explore all this.
Right, covering the physical reality of internet connection types and network types as well.
Exactly. And our mission for this deep dive is to basically demystify all that alphabet soup that goes along with it.
Oh, yeah, there's a lot of it.
So much. We're talking LANs, WANs, DOCSIs, ADSL. By the time we're done here, you're going to understand not just how you're connecting to the digital world right now, but like why engineers chose those specific technologies to begin with.
And, what physical limitations they're actually fighting against. Because we interact with this infrastructure constantly, right? Whether you're streaming this audio, working from home, or just checking a fitness tracker.
Right. You're actively participating in this massive, complex web of networks.
Exactly. And the moment you start looking at the actual physics of how your email gets from point A to point B, it's just mind-boggling. We all expect data to flow instantaneously, but there are massive geographical hurdles making that happen.
Yeah, we totally take it for granted. So to understand how this invisible web is built, let's start with the physical pipelines.
The terrestrial wired connections.
Right, the stuff that delivers the internet to our homes and offices.
Yeah.
If fiber optics are essentially light speed, the ultimate standard for data transmission, why isn't it just everywhere? Why are we still messing around with old copper wiring?
Well, it really comes down to the staggering cost and just the sheer physical labor of laying new infrastructure. I mean, fiber optic cables use actual pulses of light to send massive amounts of data.
Which is incredibly fast.
Right. Oh, incredibly. Through these microscopic glass or plastic strands. And because it uses light instead of electrical signals, it's immune to electromagnetic interference. So it's the most efficient way to transmit huge amounts of data over really long distances.
But I'm guessing the financial barrier to entry is just enormous.
It is. It's totally prohibitive in a lot of cases.
Because laying new pipe under existing cities can't be cheap at all.
Not even a little. The fiber cable itself costs way more than copper. And then you have these specialized lasers and receivers required at both ends, which are really expensive.
Oh, right. You need the hardware to actually read the light pulses.
Exactly. And, if a construction crew accidentally cuts a fiber line, splicing those microscopic glass strands back together is a highly specialized, very costly operation. It's not like just twisting a copper wire back together.
That makes total sense.
Yeah, so that's why traditionally you'd really only see fiber used for massive corporate networks or what engineers call sonnet rings.
Sonnet rings.
Yeah, they're these ultra-high-speed loops of fiber connecting entire metropolitan areas together.
But, I mean, I've definitely seen internet providers advertising fiber to the home recently. I feel like it's finally making its way down the standard residential street.
We are definitely seeing that expansion, yeah. But here's the catch. Very often, that connection doesn't stay fiber all the way into your living room.
Wait, really? Where does it stop?
Well, a provider might run a fiber line to, like, a box at the end of your street, or maybe a conversion box on the side of your actual house. But from that box to your laptop, it usually converts back into the standard pre-existing copper wiring hidden inside the walls.
Okay, let's unpack this idea of copper wiring, this specifically broadband cable, because this is what so many people rely on for their daily connection.
Absolutely.
Like, I look at my internet bill and it always says, do ics on it? But physically, this is the exact same copper coaxial cable that was originally laid down decades ago just to bring TV channels into a house.
Yeah, that is the one. And, broadband is the critical concept there. In networking, broadband just means the system is capable of carrying multiple different frequencies on a single physical wire, all at the exact same time.
I always like to think of a broadband connection like a massive multi-lane highway.
Oh, that's a great way to picture it.
Yeah, so you have cars, which represent your internet data, and then you have trains representing your television video, and you have bicycles representing your voice communications.
Right.
And all of them have their own designated protected lanes running side by side at the exact same time on the exact same road without ever crashing into each other.
That highway visualization captures the physics of it perfectly, and that DATO CSIS standard you mentioned earlier.
Right, data over cable service interface specification, a real mouthful.
Yeah. Terrible acronym, but it's basically the set of traffic laws that governs how all those vehicles share the road. Depending on which version of DOCSS your local cable company has actually upgraded to, you can get incredible speeds over that old copper.
Like how fast are we talking?
Well, ranging from, 50 megabits per second all the way up to 1 gigabit per second or even higher now.
But cable isn't the only copper hidden in our walls, right? We also have traditional telephone lines, which is where DSL comes into play.
Yes, the digital subscriber line.
Yeah.
And what's fascinating here is the sheer ingenuity required to make DSL or cable internet function at high speeds. I mean, you have engineers looking at these unshielded telephone lines that were laid down decades ago just to carry analog voice signals.
Just basic phone calls.
Right. And they somehow figured out how to manipulate those old copper pipes to deliver high-speed digital data instead. It is a really stark contrast to the pure, purpose-built efficiency of fiber optics.
Now, when people talk about DSL, they usually call it ADSL. The A stands for asymmetric, right? I assume that means the traffic isn't flowing equally in both directions.
That's right, and it's a very deliberate design choice. The engineers know that the average internet user consumes vastly more data than they produce.
Oh, sure. Like streaming movies.
Exactly. You're streaming a 4K movie, which pulls massive amounts of data down to your house, but you're only sending a few tiny clicks and requests back up to the server. So ADSL is asymmetric to strongly favor downloading.
Got it.
You might have, say, a 200 megabit per second download speed, but only a 20 megabit per second upload speed.
But I've heard DSL has this massive geographical Achilles heel. It seems like if you live just a little too far out of town, the provider will flat out tell you that you can't get it. Why does the physical distance matter so much?
Well, it's because copper wire is not a perfect conductor. Electricity is subject to resistance.
Or right, the physics of it.
Yeah. As an electrical signal travels down an unshielded telephone wire, it constantly loses energy. It basically encounters electrical friction.
Oh, wow.
Yeah, so over a few hundred feet, the data is totally fine. But when you start pushing that fragile pulse over thousands of feet, the signal physically degrades. It gets tired and garbled. In the industry, they call this attenuation.
The signal is literally just fading away into nothingness.
Precisely. To use DSL effectively, you absolutely must be within about 10,000 feet of the telephone company's central office.
10,000 feet. That's not even 2 miles.
Right, it's very short. If your house is located, say, 15,000 feet away, the high frequencies used for data have degraded so severely that the connection just drops off a cliff. It becomes entirely unusable.
So what does this all mean for someone who lives out in the country, past that 10,000-foot limit? I mean, digging trenches to lay expensive fiber for one single farmhouse is obviously out of the question for any internet provider.
Yeah.
How do we reach the unreachable?
That is where you have to abandon the physical wires entirely. You shift from terrestrial infrastructure to wireless lifelines, and the most historically prominent option for remote areas is satellite networking.
Bouncing a signal to a satellite hovering in space and then all the way back down to Earth.
Exactly. It guarantees that if you are anywhere on the planet with a clear view of the sky, you can get a connection.
Which is amazing.
It is. And the speeds are highly functional, routinely hitting 100 megabits down and 5 megabits up. But the physics of sending a signal into space introduces a massive hurdle, and that's latency.
Right, the delay between when you click something and when it actually happens on screen. But, I mean, light moves at 186,000 miles per second. Why is there a noticeable delay?
Because of the sheer distance involved. A traditional geostationary satellite sits roughly 22,000 miles above the equator.
Wow.
Yeah, so when you click a link, your request travels 22,000 miles up to the satellite, then 22,000 miles back down to a ground station on Earth.
Oh my gosh.
Then the website responds, sending the data 22,000 miles back up to the satellite, and finally 22,000 miles back down to your house.
That is an 88,000-mile round trip just to load a single web page.
Exactly. And you simply cannot code your way out of the laws of physics. Even at the speed of light, that physical journey takes time. It results in about half a second of latency on every single interaction.
Which doesn't sound like a lot in everyday life.
No, but in the realm of computer networking, a 500 millisecond delay feels incredibly sluggish. It makes real-time video calls super frustrating and fast-paced gaming virtually impossible.
Though I know newer systems like Starlink are trying to bypass that specific physics problem, right? By putting the satellites much closer to Earth in a lower orbit.
Yeah, it drastically changes the math. By operating in low Earth orbit, Starlink cuts that massive 88,000-mile trip down significantly, which reduces latency to just 25 to 60 milliseconds.
That's a huge improvement.
It is. But any satellite system, whether it's high or low, faces an environmental challenge. You need a direct line of sight. And if a dense, severe thunderstorm rolls in, the physical mass of the water in those clouds can absorb and disrupt the signal.
I've heard of that. The industry calls this rain fade, right?
Yes, exactly. Rain fade.
So what does this all mean for someone living completely off-grid? Like if you run a business from a rural location and a heavy summer thunderstorm can trigger this rain fade and knock you completely offline, that doesn't sound like a viable permanent solution.
No, it can be really tough.
Are there other options out there that don't rely on the weather so much?
Well, it highlights the central trade-off of remote geography, right? In isolated areas, connectivity is always a balancing act between accessibility and reliability. But satellite isn't the only wireless solution. You can also leverage cellular networks.
Like the exact same infrastructure that powers our mobile phones.
Exactly. Providers divide the physical geography into overlapping cells, each serviced by an antenna.
And we use this all the time, right? Like if I'm traveling, I can just create a one-to-one connection between my laptop and my phone.
Yeah, that's called tethering. But if you need to provide access for multiple devices simultaneously, you turn your phone into a mobile hotspot.
Right.
However, if you're looking for a permanent, robust home connection without relying on a tiny smartphone, you're going to look to WISPs.
I see that acronym pop up a lot in the materials, but what exactly is a WISP?
It stands for Wireless Internet Service Provider. It's essentially fixed wireless internet. So instead of pulling a physical cable into your house, you mount a dedicated antenna on your roof and point it directly at a local provider's tower.
Oh, okay. And what kind of signal is actually traveling between that tower and my roof?
It varies depending on the provider. Some WISPs use a highly directional, meshed 802.11 network.
Wait, 802.1, then that's just standard Wi-Fi, right?
Exactly. It's the exact same Wi-Fi technology you use inside your house, just amplified and beamed over miles. Others might harness a 5G home internet signal from a major carrier, or they might use specialized proprietary radio waves.
It is fast.
Oh, yeah. The key is that they can deliver anywhere from 10 megabits to a blistering 1,000 megabits per second, basically bridging the gap for rural users without laying an inch of copper.
Okay, so we've got this incredible fire hose of data finally hitting the side of the house. We brought it in from space, or over a copper wire, or via a WISP tower.
Yep, it arrived.
But my laptop isn't plugged into the side of my house. Once the data arrives, how do we actually categorize the internal networks to distribute it?
Well, network engineers categorize architectures primarily by geographic scope. The smallest, innermost boundary is the LAN, the local area network.
So this would be the network restricted to my specific house, or maybe a single floor of an office building.
Yes. And because a LAN covers such a tiny, physically controlled area, it generally operates at the absolute highest speeds.
Makes sense.
If you have a computer hardwired into an Ethernet port in your wall, you are utilizing a LAN. If you are sitting on your couch connecting via Wi-Fi, you're on a WLAN, a wireless local area network, which utilizes that 802.11 wireless standard we talked about.
I always like to visualize these network boundaries as a set of Russian nesting dolls. Your home WLAN is the smallest doll, but when you step outside your house and need to connect an entire city together, you step up to the next doll, the MAN, or Metropolitan Area Network.
The MAN definitely covers a single large geographic area, like a whole municipality. And, well, while the nesting doll is a decent-sized comparison, I'd push back slightly on the analogy.
Oh, really? Why is that?
Because a nesting doll implies the networks just sit neatly inside one another. But in reality, moving data between these different networks is highly complex.
How so?
Well, let's look at the metropolitan area network. Historically, connecting buildings across a whole city required highly proprietary, clunky technologies. But recently, they've heavily standardized on something called Metro Ethernet.
Here's where it gets really interesting, though. When I think of citywide networks, I just assume the massive telecom monopolies control all of it. But I was reading the source materials, and local city governments are actually major players in building metropolitan area networks.
Yes, they absolutely are.
Wait, so my local city hall is acting like its own telecom provider.
Yeah.
They're just laying their own internet pipes right under our feet.
They are.
Okay.
And it makes total economic sense when you look at the logistics. The single most expensive part of building a network is securing the physical right-of-way to dig trenches.
Oh, of course.
But a city government already owns the physical streets, the sidewalks, and the underground conduits. So rather than paying a fortune to lease bandwidth from a private telecom company, the local government will often just lay their own municipal fiber optic cables while they're doing road work anyway.
That is brilliant, just doing it while the street is already torn up.
Exactly, creating their own self-sufficient man.
But eventually, that city government needs to send an email to a different state. And that brings us to the largest boundary, right? The WAN, or Wide Area Network.
The WAN is massive scale. It connects smaller networks across cities, countries, and even the entire globe. But if we connect this to the bigger picture, it explains why a WAN is inherently slower and way more complicated than your local LAN. Going back to your nesting doll analogy, it's not just a bigger doll. Moving from a LAN to a WAN is more like driving out of your quiet neighborhood cul-de-sac and trying to merge onto a chaotic international border crossing.
The rules completely change.
Entirely. It is not just the massive physical distances that slow a WAN down, it's the complex routing protocols.
What do you mean?
In a local network, finding a device is pretty easy. On a global WAN, every single time a packet of data hits a router, that router has to open it, inspect the destination IP address, search through a colossal database of routing tables, decide the most efficient path, and then send it on.
And doing that thousands of times across the globe must create a massive bottleneck.
Oh, absolutely.
So how do engineers speed that process up across these massive terrestrial and non-terrestrial lands?
They use brilliant routing protocols like MPLS, which stands for multi-protocol label switching. Instead of forcing every router to look up directions manually, MPLS slaps a digital shipping tag, basically a preset label, onto the data packet the exact moment it enters the WAN.
Okay, so it already knows where it's going.
Exactly. When that packet hits the next router, the machine doesn't have to look up the IP address at all. It just scans the label like a barcode and immediately forwards it down a pre-established path. It creates an incredibly fast, highly efficient lane right through the chaos of the global internet.
Okay, so we've zoomed all the way out. We understand how a WAN connects continents. Let's zoom all the way back in past the LAN. I want to talk about the absolute extremes of networking.
The really small stuff.
Right. Starting with a network that is literally attached to our physical bodies.
You're referring to the personal scale, the PAN or personal area network. These are extremely localized networks designed strictly for devices physically adjacent to the individual user.
So all these wearable fitness trackers I have, and like my wireless earbuds, they must be creating a massive data traffic jam on my home Wi-Fi network, right?
Actually, no, they aren't using your Wi-Fi at all. They operate on a completely different standard.
Oh, really?
Yeah. If you are using Bluetooth, infrared, or near-field communication to sync your smartwatch to your phone, or maybe connect your smartphone to your car's audio system, that data is traveling exclusively over a personal area network. It's a tiny, localized bubble of connectivity that just moves with you.
But those devices are constantly gathering biometric details, heart rates, step counts, sleep data. Where does that massive fire hose of tiny data points ultimately go?
Well,
Actually, that perfectly sets up the other extreme, doesn't it? The massive repository is designed purely for storage, known as a SAN, a storage area network.
exactly. A SAN is a colossal repository of storage space, but the crucial engineering detail is that it is isolated on its own ultra-high-speed network.
But why does it need to be isolated? If it's just storage, why not just attach it to the regular local area network with everything else?
Because of the sheer volume of data being moved. If a massive corporation is backing up terabytes of video files or financial databases, you do not want that heavy traffic bogging down the regular LAN while normal employees are just trying to send basic emails.
Oh, that makes sense. It would crash the whole system.
Right. The SAN requires its own dedicated high-capacity pipeline. But despite being a massive, complex network in a remote server room, the engineering magic is that to the end user, a SAN looks and feels exactly like a local hard drive sitting right inside their computer.
And it achieves that seamless feeling by using something called block-level access, right?
Yes. Block-level access is the defining characteristic of a SAN. Instead of treating a file as one massive, unbreakable chunk of data, the network breaks it down into small blocks.
You know, the best way to picture this block-level access is to imagine having a high-speed dumbwaiter connected directly to a giant underground library archive.
Okay, I like where this is going.
Right, so if you want to change one single word in a heavy 1,000-page encyclopedia,
Yeah.
the old way, basically file-level access, would be hauling that massive, heavy book all the way up the dumbwaiter, erasing the word, and then hauling it all the way back down.
Which is wildly inefficient.
Exactly. But the SAN system lets you use the dumbwaiter to quickly swap out just that one single page, leaving the rest of the heavy book exactly where it is.
That illustrates the efficiency perfectly. You're only moving the specific block of data that actually changed. This raises an important question, though, when you put these two extremes side by side.
Quite extreme.
The pan and the SAN.
Mhm.
You have the pan generating this continuous, massive influx of tiny data points from billions of personal wearables globally. All of those individual heartbeats and sleep cycles have to be routed, aggregated, and stored securely.
Right.
It is the explosion of the localized pan that increasingly necessitates the heavy-duty, isolated storage capabilities of corporate SANs. They are literally two ends of the exact same data pipeline.
It really is an incredible, almost unbelievable journey when you step back and look at the physics of it all.
It's staggering.
I mean, a piece of data can originate in a colossal storage area network using block-level access, travel at the speed of light through multi-wavelength fiber on a global WAN, get scanned by an MPLS shipping tag, jump onto a citywide metro Ethernet man.
Right, and then get pushed down a neighborhood DOCSIS copper cable.
Or beamed 22,000 miles up to a satellite. And eventually arrive on the Bluetooth personal area network, connecting your phone to the exact earbuds you're wearing right now.
And it executes that staggering physical journey millions of times a second so smoothly that we just get annoyed if it takes longer than half a second.
And that is the true power of understanding this hidden architecture. You are now armed with the vocabulary and the physical reality of the digital world.
Absolutely.
The next time you are setting up a mobile hotspot or, the next time you find yourself groaning about a sluggish internet connection, you won't just be blindly frustrated. You will know exactly where those physical or wireless bottlenecks might be hiding.
Whether it's copper wire attenuation, the physical distance of satellite latency, or just a slow WAN routing protocol, it gives you a profound appreciation for the infrastructure all around us.
It really does.
And as we look to the future, it leaves us with something pretty fascinating to ponder. As Starlink and lower orbit satellites continue to reduce latency, and as 5G cellular WISPs become incredibly robust and capable of gigabit speeds, what exactly is the end game for traditional copper lines?
Yeah, that's a good question.
Will the physical coaxial cables and old telephone wires currently buried under our streets and yards eventually become obsolete relics? Will the terrestrial pipelines be completely replaced by an invisible, highly resilient wireless web beaming down from space and towering cellular arrays?
It definitely makes you look at the walls a little differently, doesn't it? Knowing that invisible architecture humming around you is always evolving. Keep these physical realities in mind the next time you log on. Until next time, keep looking past the surface.